So I've been talking a little bit about the way that the traditional or classical physics doesn't explain this. If you think of light as being a wave, then it doesn't really explain what's happening. And so the photoelectric effect is known for the fact that it kind of justifies or proves the use of a particle model of light, okay, because it's the only way to explain it. So let's have a look why it's so important. So to go back to the original idea, so we've got our electron trapped in this potential well over here. There's our electron stuck down there, and it has to be freed. And we know that if we can overcome the work function, then it will be free and we'll have some kinetic energy. So I won't go through all that stuff again there. Now, according to classical physics, according to wave physics, okay, they say there should be no cutoff frequency. According to classical physics, okay, according to classical physics, if you shine light long enough at it, so we keep shining our light at it, okay, we just keep shining light on it all day. According to classical physics, if you leave that enough time, the energy that's being transmitted from that light should build up, should build up, should build up, should build up, and eventually pop, the electron should be free. But that does not happen. Okay, so classical physics is completely wrong. So classical physics suggests that the frequency is irrelevant. Okay, is irrelevant. In other words, shine enough light, over time, shine enough light, and it should eventually free the electron. That kind of makes sense, doesn't it, from an intuitive sort of way? If you're adding energy to something, you keep adding energy, and eventually, bum, 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 and it's got enough to do what it needs to do to escape. Okay. The only problem is, though, is that it just does not work. This is absolutely experimentally, you can demonstrate it is wrong. Okay, and in fact, what does happen is it's all to do with the frequency. If F is less than the threshold frequency, no electron is released, no matter how long you wait. All right, so no matter how long you wait, if the frequency is too low, which means that the energy of the photon is too low, it just won't happen. You can shine photons on it all day long, but it will not happen. However, if the frequency is greater than or equal to the threshold frequency, the electron is emitted instantly. Okay, so none of this business about waiting for the energy to build up. If you're over the threshold frequency, boom, straight away. If you're below the threshold frequency, forget it. It's not going to happen. You could wait there, as long as you like. And it continues. There's one other interesting assumption that classical physics makes, which just is not borne out by the experimental evidence. It's interesting because the more we go into this, it does raise very big questions. I mean, which model is correct then? Is the wave model, does this mean the wave model is rubbish? Does it mean that the quantum or the particle model takes over? And the answer is no. Both models work in different circumstances. It depends how you want to describe light. I mean, what is light at the end of the day? It's just light, and you can use different ways to model it. So sometimes the wave theory works, the classical one works, sometimes the quantum one works. Okay, so it's very, very mysterious, actually. Okay, so there's one other thing. According to classical physics, they say this. Look, let's assume that we've got some light shining, and it's enough to free the electron. It's enough to free the electron, and the electron comes out like so. Okay, so we'll assume that the effect is all working, everything's fine. Well, what the classical physics suggests is that if we, whoops, wrong color there. According to classical physics, if we just increase the intensity of the light, so in other words, if we increase the brightness of the light, keep the frequency the same, it's still blue light or whatever it is, but we just shine lots more on, according to classical physics, they say the electrons should have more kinetic energy. So the classical physics says that, look, if you increase the intensity, now when we say that, I mean brightness, you can just think of it as, okay, when we increase the intensity, the brightness of the light, okay, they say that the electrons should have more kinetic energy. So they say, look, it's obvious. If you increase the brightness, you've got some blue light shining, but if you make that blue light brighter, well, then there's more energy. So therefore, the electrons should be pinging away faster with more kinetic energy. Guess what? That does not work. In fact, what happens is this. If you increase the brightness, intensity is the word that's used, actually. I should write intensity. If you increase the brightness or the intensity, okay, the kinetic energy of each electron stays the same. So you can make it brighter, the kinetic energy still stays exactly the same. However, there are more electrons released. So let's look at the difference. The classical physics model says that as we increase, if we just make it brighter, this light, the electrons should have more energy, more kinetic energy. Whereas what really happens is each electron has the same amount of kinetic energy. The only difference is that there are more of them. Okay, there are more electrons released. So the quantum model fits with the evidence. The classical model doesn't. So what that really means is that when we increase the brightness of a light, okay, let me just get rid of some, I'll just clear the screen and then we can talk about this in a bit more depth. So what that really means is that when we increase the brightness of a light, what actually are we doing? You see, according to classical physics, we're just, okay, there's just more energy, okay, and that's that. Whereas what we're saying in the quantum model here, the one that uses particles, what we're saying is something else. What we're saying here is that imagine if this is a source of light, okay, and that source of light, when it fires out light, it's firing out lots and lots of particles. Okay, it's firing out particles. Now, each of those particles, very important, each one individually has this much energy, HF. When we make the source brighter or more intense, we're not increasing the energy, we are just making many, many more of these particles being released. So a brighter light is showering you with many, 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 many more particles. Okay, whereas a dimmer light has got less of them. But if it's the same color, each of those individual particles that I've drawn, each individual particle here, each individual particle has an individual HF, and the photoelectric effect is about individual light particles knocking out individual electrons. Okay, it's not about the sum of those particles. So this makes sense. If we make the light brighter, there are just more of these photons, therefore more electrons released. But each electron still obeys the rule like this, as we were talking about. So the kinetic energy does not change for each one because we're dealing with it on an individual basis.